Welcome back. Today we're going to do the theory behind Lab 10. We're going to do a lab here in 445L with introduction to control systems. And so there's a little bit of theory here in Chapter 6 associated with the pulse width modulation. Embedded systems use control for a lot of applications. So whenever your device has to both input and output to the physical world, that constitutes a control system. So if we're measuring things and we're affecting change to things, it's a control system. Sometimes the human is in the loop. In fact, that's so prevalent, that's what it's called, human in the loop. And the control system involves a human in some way, whether it be trying to drive down the highway at a constant speed or landing your airplane on top of the aircraft carrier, building things in industrial environments, pacemakers, trying to keep people alive. There's a lot of control systems where embedded systems affect the behavior of the world. Okay? So here's some terminology. The thing that I'm trying to control is called the plant. Okay? In our case, the plant is the motor. Okay? The motor's spinning. It might be the human if it's a pacemaker. It might be the manufacturing system. And then we're going to have both inputs and outputs. So we're going to acquire some information about the plant. As we saw last time, we're going to measure the rotational speed of the DC motor. Okay? And then we will have an expected performance. In our case, I want to spin at 30 RPS. That'll be our expected performance. And then we're going to generate outputs using the actuators to adjust the power to the motor to bring it closer to 30 rotations per second. We'll see when we're done, there'll be some performance measures, how the accuracy is just like thermometer accuracy. The difference between actual temperature and measured temperature is called accuracy. Again, the difference between the desired speed and the actual speed is called controller error. Another parameter that I don't care about, second parameter I don't care about in Lab 10, please make the motor spin if I don't care what your accuracy is, and how fast does it respond to change. I got a demo and I'll show you when I increase the set point from 30 RPS to 40 RPS. The question will be how fast will it respond? And so if this is the desired speed here, and this is the actual speed, there will be a transient response to changes either in the set point or changes in the friction. You start going uphill, you start going downhill. And I would like it to be stable. A unstable system is one which gets so oscillated. It has so many oscillations that it basically breaks itself. We're going to use closed loop. That's the essence of Lab 10, is to feed this tachometer back in to the system to affect a change. So it's called feedback, and we'll see some choices for it. Okay, so here's the block diagram. Again, in Lab 10, the actuator is the two middle, right? If you think of the three wires, the two middle wires here, pins 2 and 3, are the actuator. We're going to drive power across those pins. That'll make it spin. That'll induce a force on the motor. This is the motor. And then this is speed in RPS. And then we're going to use the tachometer to measure speed. Now in our case here, we're not going to use an analog interface. We're going to use input capture. Right? We're going to use input capture and measure we're not going to use we're going to use that analog interface, but we're going to use input capture. And then the fun part, remember I remember what I told you to do last time with your lab partner? Who does the tachometer? The good one with circuits? Yeah, you're pointing at each other. Now, who wants to do the fun one? The other half of this is the fun part, and that's the writing the control software here to take the difference between the desired value here. X star is the desired. and the measured, and use that error in some cute and clever way to adjust the duty cycle back to the system. There are some controllers that are open loop. There are some controllers that are open loop. We saw the stepper motor is often deployed in an application with open loop. I like my example of the toaster. How do you make the most beautiful toast? Right? You put the bread in the top and you push the button. How do you make the best popcorn? You put the thing in the microwave and push the popcorn button. Okay. Now, it's open loop because unless you unless you consider the human in the loop, right? It's not black enough, it's not black enough, it's not black enough, and over a couple of days you get the toast just black enough. That's a closed loop system with the human in the loop. But typically we think of a toaster as thou shalt toast for 90 seconds and then pop. Okay? And so open loop is often not appropriate because of the problem of disturbing forces or noise to the system. So in most applications of trying to spin motors at a constant speed, we can't just predetermine the proper duty cycle and then generate this without looping. Okay. So here's some theory. Okay, this is going to be on the test, by the way, this next statement. If you can write a linear equation, that's 313 code for a first order differential equation, right? So if you can model the physical plant with a linear differential equation, so if you can write the behavior of the motor in a way such that it has a transfer function converting power into speed. Okay? And this transfer function is a simple one. It's a first order, that's the equivalent of an RC circuit, right? So it has a gain and a exponential transient response. Okay? So this is the equivalent of an RC circuit, this transfer function. But if you can write a linear equation for the physical plant, and nobody ever can, by the way, okay, so this whole thing is a little bit obsolete. If you can write a linear equation, then I can write equations for everything. Okay? I can write equations for the tachometer. Okay? What is the behavior, what is the relationship between the speed in RPS and the period or the frequency in digital form? Well, we saw that, right? That F equals, I'm going to call it X, right, times 4. Okay? So that's the behavior of our tachometer system. The frequency measured here is a linear function of the speed. Okay? So again, that's a linear function. The subtraction function, we're going to take the expected value, the desired value, and subtract off this measured value to get error. Okay? That's a linear equation. And so if everything, we saw this equation here, which wasn't quite linear, but I wrote an equation for you. You remember the equation for power equals voltage times current times duty cycle. Right? The power into the motor is where U is going to be H, okay? And H plus L is a constant, okay? So H is the duty cycle that we're going to plug into the pulse width modulating program to set the duty cycle. And H plus L is the period of that output, and it's constant. H plus L is constant. And if the friction is stable, if the friction is constant, and if your this one is fairly constant, right? That's the 5 volts minus the VCE of the Darlington. But if the friction is constant, then the I will be constant. But I'm going to be the first one to tell you, this is not linear either. Okay? The plant's not linear, the actuator's not linear. But if all of these things were linear, I could develop an equation for the controller using that same linear behavior. Again, this is a second order differential equation now, okay? Because it's got both a 1 over s and an s, right? So that becomes a second order differential equation. And I'll show you the software for that equation in a second. But if I were to be able to write my controller in 313 mode, in Laplace mode, I can now solve the entire system, which includes both the actuator and the plant and the sensor and the state estimator and the PID controller and the subtractor as a gain, if you'd like, between the desired speed and the actual speed. Okay? I can write an equation for this. And I can solve this in Laplace domain and get whatever response you want by adjusting these three parameters. Now they have names. This is called the proportional. This is the derivative, and that's the integrated, and we'll see them in a moment. The trouble is, other than the tachometer, this thing is highly nonlinear. And therefore, we're going to tune it, we're going to play with it, we're going to wiggle the knobs until we're happy. Question?
So if everything is linear, doesn't that mean that all the frequencies, you just put in a sinusoid or something, it would be always the same?
Okay. Okay, so the definition of a linear system, if I excite a linear system with a frequency of 10 hertz, all the signals are 10 hertz. Yeah.
Yeah.
Yeah. Yeah. But we're going to see the motor in a minute, okay? And it's not linear, because I can adjust the duty cycle from 0% to 5%, and it doesn't do anything. No respect. I go to 10%, it's still sitting there doing nothing. And I get to 25% and it pops up real fast. Okay? So it is a nonlinear system, okay, that cannot be adequately described with a differential equation. Did I answer your question? Yeah, it's a linear system. I don't mean y equals mx plus b. I mean a linear system in a 313 stent, that it has basically behaves in a model sense like a resistor, a capacitor, or an inductor. Right? It has a second order differential equation. Right? Again, if you see this in physics, what would that look like? Give me an example of a mechanical system that has can be described by a second order differential equation. Physics. This is physics 1. This is high school physics. Well, except for the differential equation part.
Spring.
A spring. Okay. F equals m dx dt squared plus the friction dx dt plus the spring x, okay? Such that we have this is a linear system that's describable by a second order differential equation. It can be a third, in the context of control systems, it can be a third order or fourth order, but it needs to be translatable to sequences of s's, s squareds, and s cubed, that kind of thing. So if we were to have such a system that behaved this way, like you were trying to make a pendulum clock, okay? You could make a pendulum clock with a controller. All right. Well, let's translate to how this would look like in software. If I were to implement a proportional integral derivative controller, my first step is to calculate the error, which is the difference between the desired state and the measured state. So this is the desired, okay, 30 RPS, and this is the measured, whatever, 30.1 RPS. And again, the output of the controller is this duty cycle, H, which will vary between some minimum number and some maximum number. In other words, the duty cycle is going to vary between 0% and 100%. Right? And if I make a mapping between the error and the h that has a direct or proportional property, that's called a proportional term. If I take the error and use it to incrementally add or subtract, then that's called an integrative. If I take the derivative of the error, okay, and let me give you an intuition for this. Okay, let's talk about driving 55 on the turnpike on I-35. Okay, no traffic, so you're going 55, and think about the control system with you as the controller. Okay, what are your inputs and what are your outputs? Okay, what are your sensors for driving on the turnpike, trying to go 55 miles per hour? What are your sensors?
Your eyes.
Yeah, your sensors are the eye, but what are your sensors measuring? Yeah. What are you measuring with your eyes?
Speed on the tachometer.
The tachometer. You're looking at the dial or the number and you see a number, 54, 53, 52. Okay? The controller is your brain. Okay, so what is the actuator? What is the output of this system?
Your foot.
Your foot onto the accelerator. Okay, and so interesting is, what do you do if you're going way too slowly? You're daydreaming and now you're down to 30 miles per hour and you should be going 55. What do? You put your foot down. Now here's an interesting question. Are you implementing proportional or integrative? So here's what in your mind, are you pushing or pulling on your foot? Okay, that's integrative because you're making a change to add a lot or subtract a lot. Or are you saying, oh, I shall go to 14.2 centimeters on the foot dial? In your brain, you have no knowledge of exactly where the pedal is. You see that? You have no knowledge that you're 14.1 centimeters from the floorboard. Okay? At least I don't. Okay? I'm not looking at it. I'm just feeling it with my foot. There's no sensor on your foot to tell you really how far down you push. You're just going to stomp on the gas because you're going way too slow. And that brings you to the fact that I have a very large error. Okay? I have a very large error. Now here's another thing about what you're doing. How fast do you look at the tachometer? By the way, you're going 55 and your eyes are looking at the tachometer. How fast are you looking at it? You're not always looking at it. You'd be in the bushes. Eyes on the road. 10-2. That's Dad speaking, right? 10 and 2, eyes on the road. You're sampling it, okay? Once a second, once every 5 seconds, I don't know. Right? You're sampling it. Now, it's just a computer, so we're going to sample it at a constant rate. That's delta t. And then every delta t, I'm going to look at it and decide if and now what do you do if you're 54.5 degrees, miles per hour? You're trying to go 55 and you're 55.5. You're just off a little bit. What do you do with your foot? Well, okay, maybe nothing. That's close enough. You might go, let's go 57, 58. Now what do? Ease off, right? You see, that's an integral controller. If the error is small, if the error is a little bit too, if I'm just a little bit too fast, I am going to decrease. Now look at the sign of the word error. Because this is 55 and this is 57, in that scenario, E is negative. So what can you tell me about the sign of Ki? In your brain, it's positive, okay? And so this brings me to the only one thing you got to remember. Get the sign right. Just saying. Imagine the guy who flips the sign on that controller, right? We're talking about them on the news, right? I'm going too fast, so I'll slow down. I'm going too slow, so I'm going too fast, so I'll speed up. I'm going too slow, so I'll slow down, right? no matter where you hit, it's unstable. Okay? So this controller becomes unstable if you get the sign wrong. Okay? So that's the first thing I got to tell you is get the sign right. Make sure it goes faster if it's going too slow and slower if it's going too fast. And whether that number is a 2, 3, 4, 5, 6, or 7 is not going to matter next week, by the way. Okay? It'll matter, but not matter for 445L. The second thing that you got to remember for the fun part of this lab is this step right there. Make sure you have a minimum number and a maximum number so you don't inadvertently rotate around and trying to go too fast, you end up going way, way, way too slow. Let's see what else I want to say about this. Here's another scenario. What if you are you're trying to go 55, you're already going 57, but you notice that where's my, you notice that the error is negative. Okay? You're going too fast, but the error is negative. What does that mean? I'm going too fast, and I'm slowing down. You see that? If I'm already going too fast, but I'm currently slowing down, what do you do when you're driving? Nothing. You see how these two can balance? What if you're going too fast and speeding up? You slow down even more. Okay? And that's the intuition be combining an integral term and a derivative term. Okay? An integral term and a derivative term together allows you more thought about what to do if you're away from the set point but going closer to the set point, or away from the set point and going further from the set point. Thou shalt have no derivative terms in Lab 10, because it turns out that our tachometer is way too noisy. And if you do the...
Dr. Valvan?
Yeah, sure, go on.
Could you please explain about the derivative term, say again, whatever you mentioned?
Okay, I'm just trying to give you some intuition, all right? The integral term has to do with if you have a large positive error, right? Remember, error is equal to x star minus x prime. Well, this is the desired and that's the measured. Okay? If the error is large, okay, that means you're going way too slow. So I'm going to add a large amount. Okay? If the error is large and negative, okay, I'm going to subtract a large amount. That's the intuition between the integral. The derivative term means, let's look at the four cases between, let's just make it in English. If I'm going too slow, if I'm going too fast, but I'm accelerating, or I'm decelerating. Right? If you think about if I'm decelerating or accelerating, okay? Now, because the derivative of the error, since error is a speed, right? Errors are speed in this context. The derivative of the error is an acceleration. Now, in this context here, okay, I'm going too slow and accelerating, right? I don't want to do anything. If I'm going too fast but I'm decelerating, I'm not going to do anything. But if I'm accelerating and going too fast, I'm going to double. I'm going to double the slowdown, the decrease u equals u minus large. In this context here, I'm going to decelerating and go too slow, I'm going to double plus increase my power. And from an equation standpoint, that is simply U equals U, UD equals UD plus some constant times the derivative of the speed, or the derivative of the error. And I got to get the sign right, okay? Again, I got to get the sign right. And it's a combination of UI equals UI plus a constant I times the error. So this sort of table here, where I'm going to compare both the error and the acceleration and combine them both into a single U equals UD plus UI. Did I answer your question? Yeah. And don't use the derivative this semester because of this problem here. And this is if you look at your speed as a function of time, it looks like that. And the error is huge and horrific. Centered around the correct speed. So the derivative of this noisy signal is astronomically horrible. Interesting. What does the integral do to this, by the way? The integral, another name for integral is sum. And we've seen a fancy theorem way back in lab 2. Central limit theorem is actually our friend here. The integral term really proves the integral term has a much improved signal-to-noise ratio because we're averaging, we're adding them up. And so the average of some points in this loop are indeed much closer to the correct answer. So the integral term here is pretty stable. All right, so we got to run the controller faster than the plant. There's a Valvano rule that's, you can run 100 times faster or 1,000,000 times faster, but this is why the people in the back seat of your car need to be quiet. You ever have backseat drivers? Shut up back there. I'm in front. I got the hands on the wheel. I'm doing what I want. You don't want to put people in the back to drive because you need to update fast enough. It takes too long for the person in the back to say, would you please go faster? Would you please, you're going too fast, would you go slower? You know, whatever they're saying in the back is, they don't have their eyes on the, you know, if you let the person in the back control the speed, you are running way too slow and you're going to oscillate from 100 to 0 miles per hour because you know, you're going too fast, you go down to 0. Oh, now you're going too slow, and then you go to 100. Oh, now you're going too fast. And there's a rule right there. Your controller, the thing that's running the feedback loop, needs to be faster than the plant itself. Or you have chaos. So your plants are about 10 seconds, tenth of a second, sorry, 0.1 second, and you're going to run this at about 100 hertz. Okay. So we're going to, the other problem is you can't run faster than the sensor. Okay. You know, you ever thought about, I always thought about, you know, I got my little GPS, little map on there, and I'm always thinking to myself, what if it were snowing outside and I couldn't see out the window? Could I stay on the road by looking at just the GPS? I don't know, I do too much driving. The point is I can't. For a couple of reasons. First of all, the sensor's really crappy, right? Because it's off by plus or minus 20 feet. Not good enough to stay on the road. And the second is it's way too slow. The data I get off my GPS is too slow to stay on the road. Right? The feedback loop would be, and you see that actually you can actually see that in this. If I add a delay right here, okay? What this is going to do, if you add a delay, and does anybody know what a cool way to look at this curve, this plot? by the way? Yeah, the 313 question. If you want to characterize that equation, how would you do it? Ah, come on, you loved your 313. Come
Bode plot?
on. A Bode plot, yeah. Okay. And what am I going to do is the real part. This is that whole thing, right? This is that whole equation, the entire system. I'm going to look at x star divided by, I'm looking at, sorry, the other way around. I'm going to look at the measured x as a function of x star in the S plane, the real part of S and the imaginary part of S. And what do you want to see? What are some good things? Poles and zeros, right? Where shall I put the poles?
Left.
Yeah, you want to put the poles over here. And you know what that delay does? Moves the poles over here. Something if the delay causes the poles to shift over into the wrong half, okay? And it becomes unstable. Right? So the delays are bad. But it comes down to this, and that is the sensor itself will induce a delay. It takes a certain amount of time for you to get a measurement. Right? So again, you're getting measurements potentially how much faster than it rotates, by the way. Remember, you get four oscillations on the tach per one rotation. So your sensor is by design actually faster than the thing it's spinning. That's a good thing. We'll see accuracy, stability. Overshoot's interesting. You're going to see overshoot, and that is once I set my set point, it'll go too fast. And then we have transient response, and I'll show you these two in the demo. I don't care what they are, you should just know what the terms are. Accuracy is the difference between desired and actual. Stability means does it actually spin and doesn't blow itself up. And the response time, which has actually three phases. It's got a delay phase, a slewing phase, and a ringing phase. So it has three phases in it. And I don't want to talk too much more about it, except that I'll repeat this at the end of the next lecture, and that is your sensor is the weak link here. Okay, by the way, the tachometer is the big problem. The PWM and the transistor are beautiful. It's just a tachometer, you know. And if you don't know how fast you're going, you can't possibly go for the right speed. The second is all sorts of nasty things can happen in your software. Make sure you're observing everything. This is a good application of dumping, observing, whatever, so you can see. There are a lot of knobs here. Try to adjust one at a time. Questions on the theory? Let me do a demo. All right, questions?
Doctor.
Yeah.
So you said that you are using input capture for, say, tracking the speed. So do you think it would be better if we use ADC, or is that also going to make a weak link?
Okay. Mahesh is asking, are there other ways to take that sine wave and get the speed? Okay. You could sample it with the A to D converter and do a fast Fourier transform on it, capture out the fastest frequency. Yeah, I'm not, it's, you could sample it very fast and essentially use the A to D converter to measure period, but you're not going to do it as well as every 12 nanoseconds, by the way. At 12.5 nanoseconds is the resolution of the input capture, so it will not be as good as that. And to the extent that this is noisy, it's noisy in the transducer, and it doesn't matter how you measure it, it's still going to be noisy. So if you want a better transducer, buy a better tachometer. How's that? So if some of you would like to try this with the A to D converter, help yourself, I don't care.